on with it. This is, as I'm sure most of you are aware, the standard model. This is just everything that makes up the universe. At the top in green, we've got quarks, which are sort of what makes up most of the stuff. Almost everything is made up of quarks. And then we have the other group of fermions, which is the leptons, which, as I'm sure you're aware, the electron is the only one you come across in day-to-day school. It's the only one you normally need to concern yourself with. There are the 5 others there, but these are all split into generations. So up, down, electron, and the electron neutrino are your smallest of each of the sets. And as you go up, nothing really changes except their mass. Their size is the same, their charge is the same, but their mass is bigger, and obviously the heavy ones such as topical decay to charm will decay them up. And that's why you don't normally concern yourself with anything other than these first few, because to get top quark without it decaying down requires such high energies that you only really have these particles in places like the Large Hadron Collider. But we don't know all that much about quarks, or if they even are fundamental particles 100%, because we can't look at them directly. We can shoot lots of protons at each other, and we can collide lots of things to see the fragments that come out. But quarks are bound together when they're in sort of composite particles, which is neutrons, protons, everything you normally hear about. They're bound by the colour force, which Robin will speak about that next week. But that's such a strong force that the energy required to separate 2 or 3 quarks from each other would produce an anti-quark, which would then annihilate with the quark you've just isolated, making the whole thing completely pointless. Yeah, so these are called the 6 flavors of quark. So colour and flavour, strange things. Yes, strawberry. Most of the words you'll come across don't mean what you think they mean, so we'll come on to spin a bit. But the leptons, we had a talk about neutrinos a couple of weeks ago, some of you remember. They are extremely lightweight, they don't really react at all with anything, they don't interact much. It's very hard to actually detect them or see them or know that they're there, so not really going to be focusing too much on them. And then the tau and the muon are obviously just like heavy electrons. The thing about quarks that makes them different from other fundamental particles like the bosons is that they have what's called half-integer spin. And this doesn't mean they actually spin, it's really hard to explain. It's an intrinsic quantum property of the particle. It gives them their magnetic properties, but there's no way that they could actually be spinning, because they'd have to be spinning faster than light for that to be possible, which isn't possible. So no one's really sure what spin is, so there's lots of different ways of trying to explain it, but I think we'll just leave it as it's a property of the particle, and most of the quarks will have a spin of 1/2, and it spins around the full 360 degrees if you imagine it as spin. It doesn't go back to its original position. It's such a stringent concept, but it has to go a full rotation twice to be in its original orientation. But because you have half-integer spin, the common spins associated with the quarks are up spin and down spin. And these are determined by the quantum state of the particle. And the quantum state is dictated by its quantum number, which is basically like a set of coordinates. It's a set of numbers that determines where it is in space and other properties such as its spin. And one of the fundamental laws of fermions is that no 2 fermions can occupy the same quantum state at the same time. So what happens is then this is how you get orbital patterns. Some of you will come across this in chemistry, where you have 2 electrons per orbital. This is because you have upspin and downspin. No other particle can occupy that space at the same time, because then it would have the same spin. Oh, it would have to have, the third one would have to have the same spin as one of the first 2, and therefore they'd be in the exact same particle, and that just wouldn't work because of Pauli's exclusion principle, which I would write on the board if I had a pen. No, I will. That's fine.
Is there one in the tin?
That tin, I know the tin.
The tin.
I'm psychic. Psychic. You have lessons in this room.
I actually don't know.
Right. So nice and simply, it's just the probability, with a bad symbol there, the probability that 2 electrons, in this case, will be orbiting an atom in a shell, sort of in some sort of orbital, is the probability that electron 1 is in position A times the probability that electron 2 is in position B. And then, because the 2 electrons are completely indistinguishable from one another, because they have the exact same mass, charge, speed, you have to account for the fact that the probability spin is the exact same if they were swapped around. But since no 2 fermions can be in the exact same place, you have to minus the probability that number 2 is in position A times number 1 being in position B. And because of this, if they both have the exact same properties, they have the same spin, then the first half and the second half will just cancel each other out because they're the exact same. So the probability that any 2 particles of the exact same quantum state can be in the same place is 0. And that's sort of the main point about spin, and basically all you need to know about what these things do. The next thing is why we look at them, what they actually make up. And so they sort of split in a very strange way. Fermions, the quarks and leptons, can be split into categories of hadrons, which are mesons and baryons, but the mesons aren't fermions anymore. So when you have...
Maybe we should write up all of these up. The mesons, baryons, fermions.
Yeah.
I'm getting confused.
Right. Yeah. So mesons are just a combination of any 2 fermions, but because you can't have sort of broken charge, and they all have non-integer charges as well, you end up in a situation where you must have a normal fermion and an antiparticle equivalent, so the charges add up to a number, a whole number. So 2 parts makes a meson, but they've all got strange charges. It'd be helpful if you could see those.
They have strange charges of their
weird charges. Weird. Not going to be strange. Let's not say that anymore. Right. Thank you, Robin. Up. Very simply, up charge and top. We'll just use up because we don't need to worry about the others. They have a charge of 2/3, positive 2/3, and the negative ones down strange and bottom, they have a charge of -1/3. So you get lots of different combinations, but they must all have sort of whole integer charges. So you can have up and anti-down together will make a charge of 1. And since there are only 2 of them, and it's a quark and an anti-quark, that makes a meson, which is technically a boson, which is why it's hard to explain, because there's lots of things that are in multiple categories. So. And then there are baryons, which are combinations of 3 quarks. So there's a whole load more. There are a whole load more combinations of these now, because obviously with 3, and since there's so many names for them, like different ones, but the most simple ones are the protons and neutrons, which you come across all the time. So. And so So we've got protons and neutrons. Protons are up, up, down, and neutrons are down, down, up. And you can see that if you just add up, so 2/3, 2/3, and minus third, you get proton being +1, neutron being neutral, zero charge because of the two downs and up. And this is sort of the basic, if any particle ever has some combination of up and down charges from its quarks that make these whole initial charges. So, it's sort of hard, I won't talk anymore about mesons because they are incredibly weird and they're bosons, so Robin may talk about them. Strange, I shouldn't use that. But, hadron is defined by any particle that is bound together by the strong force. So they're some weird system where they're surrounded by gluons to hold them together. So forces, Robin's going to cover that next week. But everything, you could also get what's called pentaquark. And that's a bit hazy, that area, but that's just combinations of 5 quarks to make up particles. There's a lot of areas here where it's sort of, people think it's true, but there's a lot of areas where it could just be utter nonsense and we don't know it yet. So I'm trying to not tell you anything that's completely wrong. Yeah. Said most of my points already. Another point is you end up with hadrons that are their own antiparticles. Come on to antimatter in a second. But every particle, as you can imagine, has an antiparticle counterpart. Except when you get combinations like here, where you have up and anti-down. Mesons like that, not that one specifically, can be their own antiparticle. An example is a neutral pion, which is created from an up quark and an anti-up quark, giving it a neutral charge. But if you reverse that, then you've still got the same combination of up and anti-up. It doesn't matter which way around they go, because they're all identical, except for the charge. So they become their own antiparticle. And
Up and anti-up, and they annihilate.
yes, yeah, that's the thing. You would imagine they would just annihilate each other, but for some reason they are a particle with an incredibly short half-life, but they can exist. Which seems fundamentally wrong, but you do get particles which are, you would assume, just right. Yeah, that's another thing. Is, since you can have fermions, they can't be in the same quantum state, but a spin is one of the properties of their quantum state. They have different spin that's perfectly acceptable to be in the exact same location at the same time, so they can just pass straight through each other because their spin is different, they're technically quantumly different, and so it just carries on through. All of this is a quantum system, which means most of the laws of physics just don't apply to them, and they do whatever they like. But the interesting bit is antimatter, because we've said that antimatter is the exact same as normal matter except for charge, and so they annihilate with their matter counterpart whenever they come into contact. But the problem is we have stuff, and the problem with having stuff is that means that there is the ratio of antimatter to matter is drastically wrong. Because for every quark, every particle that we have, there should be somewhere an antimatter counterpart if everything was created symmetrically like is theorized. But that means that there must be some fundamental difference between matter and antimatter, which has given rise to this huge imbalance sort of nature of the universe where we've got all this matter and no antimatter. There could be whole universes made of antimatter, but if there were, then there would be antimatter particles sort of drifting through space, which they are looking for in the AMS detector. AMS? Yeah, AMS. Yes, from the ion spectrometer. They have lots of complicated names with all very convenient anagrams. I'm convinced most of the places they sat around for a couple of hours trying to think of a good anagram to fit a name. But yes, that is one of the main things they're doing with antimatter, is looking for any particle of antimatter. If they can find an anti-carbon floating around somewhere in space, that will basically prove the existence of anti-galaxies floating off somewhere. So that is one of the things that we will be looking at while we're at CERN. Actually, we're going to the antimatter factory, where they make and store antimatter. They can store it for 7 minutes. 7 minutes.
The number changes every time.
Everyone that you talk to has a different number. I'm pretty sure Olaf said 7 minutes. So you trust him. So yeah, 7 minutes, and that's for a group of sort of 300 atoms or so of anti-hydrogen. Hydrogen would be the simplest to make, so we stick with lots of sort of 300 atoms of anti-hydrogen to spin around in a big circle, held in place with alternating magnetic current to keep it spinning around the vacuum so it doesn't destroy the lovely machine. I think no, you cannot store it in a magnet to be used as a weapon against the Catholic Church.
Why do you need a book?
Yes, go read into the news. All you need to know about antimatter. Right. So yeah, that explains sort of why, hopefully I should have explained, I'm sure I've done a terrible job at most of it. But does anyone have any questions at all about anything I've missed? Right.
I'm having an existential crisis.
Because I was going to move on to my next interesting sort of thing to consider about them, but it is just makes no sense. All of these have no size. And I said they're the same size earlier, they don't have any size. They have no dimensions, they are point particles. They have charge and mass, but they don't have a size, which means theoretically you could fit infinite numbers of them into an infinitely small space.
But adding to the how you use it.
Well, they wouldn't necessarily be in the exact same location, but they're infinitely small. So if the number of them fit into an infinitely small area, meaning that they are infinitely dense. And anything that is infinitely dense has a black hole. So we come to a problem where if all of this is true, every proton and neutron and everything that come into contact with is made up of 3 black holes. And every atom in your body is just made of millions of black holes, which obviously isn't the case. Otherwise we wouldn't be able to be here.
Yeah, there's the problem. There's the problem that happens where with stars that are imploding, as you have with neutron stars, they have a limit of how small they can be because of the exclusion principle.
Yeah.
Because if they get too small, the particles end up in the same place and that's not happening due to exclusion. So they stay at a certain size.
Yeah.
But then black holes go over.
But it's still small enough to be dense enough to create a black hole. And then you end up with a problem where you have to create extra dimensions to explain their size. One of the explanations to explain how you get infinitely small particles is to say that they are only dimensionless in our dimension. So they only interact with one of our spatial dimensions, and there could be, they could be all sorts of massive sizes in the other sort of 9 spatial dimensions that they theorize with string theory, which obviously, makes 0 sense to anyone trying to imagine around the spatial dimensions. It just doesn't work. So there are lots of problems with this theory, but it's the best one we seem to have. Because if you also think about it, you have lots of these particles which have the same charge. So you have lots of particles with positive charge crammed into the space of a proton, and then you've got a proton with a charge, and then they're all crammed together. All of these positive charges and nothing is repelling each other strong enough to break it apart. So they have lots of these bosons to sort of come up with ideas for how they don't rip, nothing like rips itself apart because of the charges. So the theory is that there is like a cloud of gluons that surrounds the quarks, and that's what keeps it in a sort of spherical structure of a proton or a neutron.
Residual strong.
Yes, residual strong force. We'll talk all about that.
It's delicious.
All those flavours. All delicious. Yes, it does get kind of complicated with flavours and the colours, especially when you get into the anti-particles. So you've got an anti-green colour, anti-blue, anti-red.
So we expect the red ones to be like
They're not at all. Yeah.
There's something that's quite like
Orange. Orange.
Yes, it's both flavour and colour.
Oh, you are just on top form today.
Wow. Right. So that sort of sums up every point that you need to know about the standard model of there's not too much detail I can give you without it getting ridiculously complicated. You know, as soon as you try and discover why they have spin or why they do this or that, it all just becomes a mess of numbers and Greek letters. I mean, this is the simplest way that I can show it. There isn't a single normal number there. So, is anyone unsure about anything? Yes. Yes.
I'm always unsure about tempting quantum mechanics.
That's pretty much the point.
Yeah. I still want to know how this maze on anti-up.
The up anti-up doesn't work.
Your description is not satisfied me.
I know. None of the stuff I read satisfied me either. It had this long rambling thing about how it was its own antiparticle, and for some reason they don't annihilate. I had the same question last year, and I still never found the answer to it. So look away. None of the places I had a satisfactory reason for why they don't annihilate, but they just seem not to. Yeah.
How did they figure out they were point particles?
You can't measure sort of anything smaller. You can't find, we haven't found anything smaller. Therefore, we assume they are fundamental particles. We assume there is nothing small on them, and for nothing to be small on them, they can't have dimensions. So it's not that they prove they have no dimensions. It's that it's just that's the theory of quarks, is that they have no dimensions. It could be, 20 years from now, they do find that all quarks are just made up of two smaller bits. So,
oh my god, so cool.
Yeah. Anyone else? You again? Yep.
It is literally as the same as
It's just probability. For now, that just means probability. I don't know why they don't use B, but it's always written as that. So I thought I may as well write it as that. So if you ever see it again, you'll know what it's going to be about. Most of the Greek symbols are used because they ran out of letters.
I just went on Yahoo Answers, and they have the question already, and the best answer is fucking song.
It just does not make sense.
It's the least satisfactory.
I know, it's horrible to not know, but the problem is no one really knows. So it's hard to give a good satisfactory answer to why these things happen the way they do. We observe them happen, we observe this stuff happening, so we go with it. Hopefully someone will come up with the answers we need one day. Yeah.
Because why not?
Not a good reason. Not a good reason at all. Yeah, I think that should be everything. It's rather a quick talk. I'm never quite sure how much people know beforehand. Some of you may have no idea what's going on. Others of you may know more than I
think I've got a little bit of information.
Have you? Yeah, found something.
I've got a list.
Read it out.
Okay, it's really not very satisfactory, but it does explain a little bit. So when you've got the quark and the anti-quark in the same place and at the same time you up and anti-up in the same place, they have such a short half-life that they don't get far away enough from each other for it to be not considered a particle. And because it's got a satisfactory whole number charge, it's got zero. So it's a compatible particle. It's possible for it to exist, but they annihilate so quickly that they don't get far away enough for it to not be considered a particle.
But so they pass each other.
And
They're
explode.
They're a particle just before they hit each other.
I'm not sure. Right?
So even though
I think that's
To be honest, it's helpful because you can categorise things. Before they had this system, every single particle, instead of just having to worry about the proton and the neutron, they ran out of vectors, they ran out of treatment words, and everything was reduced to just a scramble of like 12 Greek symbols. This makes it slightly easier. I mean, the more important ones like the up and anti-up have their own names, that's a pion. I mean, you do use these things when looking at the decay of high-energy particles in the Large Hadron Collider. So I said that the large mass ones, they break down into the smaller ones. When you collide two protons in the Large Hadron Collider, you don't just like, get a Higgs boson, you don't get something that you want, you just get a load of energy, and that just manifests itself as a particle which decays down, and you can look at it through the stages of decay. And so it's a bit like just smashing two apples in each other really hard. So instead of getting chunks of apples, you get a watermelon, and that watermelon turns into a bunch of grapes. And you can tell from the pattern of the grapes how many seeds the apple has. That's the best analogy I've heard to describe it.
Is it a metaphorical charge or is it an actual
It's the
charge?
actual charge, that's where the charge comes from.
When we consider the particle to be aiming upwards, apart from the part of they will collide because they're trying to be attracted to each other.
Yeah, they
We
will.
don't have to
They will be attracted to each other, and they will annihilate because the anti-atom is bad. I mean, that's where protons have charge because they have two or down quark. That's
There
where
are a lot of quarks on that.
quarks don't have mass.
Yeah, but
Quarks
there's
don't
three
have
of them, they
mass.
have mass.
No, quarks have mass. Quarks don't have size.
They have massive inside.
They have mass, but they size.
Trying to
No. Right, just assume it is so small you cannot see anything smaller than it. No matter how hard you try and break this thing apart, it will always be the smallest thing. You cannot divide it any smaller. We think. Which is why it's assumed to be, I mean, why I think all the atoms were completely indivisible. That's what atom means. And then they found protons. They thought they were invisible. Now they have quarks. But now they have no size. And they are just mass. And that's it. They are just mass and charge and no size. But they still have colour charge and all sorts of other properties. They also, it's very hard to understand what any information you read about these is on about because they have all sorts of strange properties and names. They do love their strange names. I mean, there is a property of a quark called its strangeness. And its strangeness is 0 for everything except the strange quark, which is 1, and -1 for an anti-strange quark. I don't know why you use this. Is it, oh yeah, that's a bit crazy. Strange, yeah, the strange quark has a -1 strangeness, and the anti-quark has 1 strangeness, and they have the same charm as well. And they're all just.
Right, you're confusing us now.
They're all just.
I was confused before I walked in.
That is just the nature of these things is you can't even look at them. The only way you can actually just find out that these things exist. There's people that have done it too that have come across this, but it's just maths. That's all you do is you go through equations and your final number comes out as +1/3, and that that somehow proves that you've had an arc clock. It's just almost pure maths, which makes no sense to anyone unless you're doing a degree. And so it's very hard to try and explain where these things come from, how they behave, and why they behave like that. No one really knows.
But I'm totally dyslexic, so
Yeah, Rob's going to try and explain all these things for the bosons.
which are better than the fermions.
They're not better at all.
They're better. They are better.
They have
Better. They're just better because I'm talking about them.
everything is made of fermions, Robert. Everything. The best.
Yeah, but if we have any bosons, we're not
They are forced. I've got Right, so apart from the standard questions of why and how, does anyone have anything that they really still cannot wrap their head around at the basic level? If not, just go through everything quickly and try and sort out some of the confused spaces.
If no one puts their hand up, I'll thoroughly impressed or immensely.
Is there anything that you don't understand, even a little?
Well, I think that's it.
When two things annihilate, they produce a lot of energy.
Yeah,
Does that energy manifest itself as a photon?
it can manifest itself in
Or just as any photon? Or does it then manifest itself as another thermal?
It can just become energy produced can theoretically become all manner of things, which is why I was saying if you smash the atoms together, you make it all manner of things, it becomes a bunch of bricks.
Good example like positive electrons and to
Oh, yeah,
He has answered how.
yeah, when you've got the electron and the positron, the anti-electron with its own fancy name, when they collide, all of the energy is used to produce two identical gamma photons. And because of the conservation of momentum, they fly in opposite directions 180 degrees. I'm still not sure about that. But the A2 syllabus assures me it does, but I have my suspicions about that. Yeah, it assumes that they fly at zero. Yeah.
It's overall system has zero momentum, so yeah, that's correct. But if you have two electrons going at high speed,
It's no way that you get 180
your
degrees.
photons will
Which is lovely if any of you are doing medical imaging.
that's like CAT scan sick crap.
It just lies to you. Yeah, it's more about let's lie. It's more
So, do we assume that these things have no dimension just because they're smaller than Planck's constant?
Can we steer away from the fact that these have no dimensions because it does just confuse things immensely?
Okay, let's ignore that. They're just tiny. They are just tiny. Once you assume they are tiny, but they have a dimension, everything becomes easy to think about. They're little, tiny little like marbles. Yeah, like tiny marbles flying about. But it's a lot harder to assume.
Then you do your nice maths, but that's
All
what
the physicists have lost
How does CERN store the antimatter?
That's a good one. Antimatter storage is kind of hard to do, but they've got a pretty good bit by now. What happens is you have, just like how you move particle around the accelerator, you have a series of magnets.
Oh, so it's just
And they have charge until it's a complete vacuum, the best vacuum they can get, obviously. They collide with a random particle, everyone's screwed. But they just use a series of alternating magnets around the ring to bend it around this big ring. It's quite a big machine. But yeah, it just bends around continuously, flying around at ridiculously high speeds, 99.99% the speed of light. And it just whizzes around for about 7 minutes. They never really explain what happens after about 7 minutes, as if it just fizzles out or annihilates. If something got in and it hit it, travelling at almost the speed of light and annihilated it, the energy would destroy you. There would be...
Oh my god! No, you're right. That's the... No, we are
Ignore certain parts of it, it's fine. Cut. It's over.